All right, chapter 22, electric charges and forces. So this is mostly concepts, this chapter. So here are the learning objectives. To become familiar with basic electric phenomena, to learn the charge model and apply it to situations involving conductors and insulators, to understand polarization and the attraction between neutral and charged objects, to understand and use Coulombs Law for point charges. We're going to use this a lot this semester, by the way. To recognize and use the principle of superposition for electric forces. That just means you add them. To begin the process of understanding the field model and the concept of a field, a force field. And then we're going to learn the electric field of a point charge. Now, I assume you've already read and understood the first 3 sections of this chapter, because it's all, concepts, so I'm going to skip most of it. So let's just review. And I'm sure a lot of you already know a lot about this charge model. So 2 kinds of charge, plus, minus. If we have like charges, what do? They repel. If we have unlike charges, what do? They attract. Okay, conductors and insulators. A conductor is something like copper, a copper wire. It just means that charge flows. An insulator, like a piece of wood, dry wood, it just means that charge doesn't flow along a piece of dry wood. That's all. So the difference between a conductor and an insulator is just the mobility of charge. So everybody pause your video and figure out the answer to this question. All right, let's talk about it. We have 2 objects, A and B. A has a net charge, B is uncharged. Based on this information, can you tell whether or not either object is a conductor or an insulator? No! Because the only thing that differentiates between a conductor and an insulator is the mobility of charge. You can charge an insulator, you can charge a conductor, so just because they are charged doesn't mean anything. Mobility of charge. All right, let's consider this. So here's the ceiling, here's an insulator, a piece of string, here's an uncharged metal ball, right? Conductor. So all of a sudden you bring a charged rod close to but not touching the uncharged metal ball. What happens? So everybody pause your video and figure it out. All right, what happens is this. The metal ball moves towards the charged rod. Now this should seem strange to you. Come on, this is neutral. Why should something neutral be attracted to something charged? That's weird, right? Well, let's talk about that now. Okay, why? So pause your video and vote. Okay, so let's see. Charges move back and forth between the rod and the ball. Totally garbage. They can't do that. The attraction is magnetic. We don't even know about magnetism yet. Neutral is a 3rd type of charge. Thus negative and neutral are opposite. That's baloney. The answer is 4. None of the above. Okay, so what's going on? Explain it. So there's 2 explanations. So there's one explanation for a conductor. There's one explanation for an insulator. So let's do the conductor. So here is the neutral conductor. Here is the charged rod. Now remember, this is a conductor, so the electrons can flow. If you have a positive rod here, what do the electrons in this metal rod do? Wow, they see a positive, so they move to the left, right? They're attracted to the left. What's left over here? The positives. So this is called being polarized. It's a shift, right? The electrons shift. So let's read all this stuff. So remember, we talked about a metal having a sea of electrons that can move, right? So the sea of electrons is attracted to the rod and shifts, right? They shift to the left. So there's excess negative charge here. there's a deficit of electrons here. So it's a net positive charge. Now look, this thing is still neutral, right? This thing is still neutral. It's just that it's been polarized. So the metal's net charge is still 0, but it has been polarized by the charged rod. Well, if you have a positive rod here, you have negative right here, what's going to happen? It's going to be attracted. So that makes good sense. All right, so that's a conductor, right? A neutral conductor. Now let's talk about a neutral insulator. Okay, so here's the external charge. You can think of the charged rod. Here's a neutral insulator. Now remember, insulator. So the mobility of charge is very tiny. So what happens? Well, most insulators, or many insulators, consist of polarized molecules or atoms. What's that mean? So here's water. Water is a polarized molecule, or whatever, atom. So in chemistry, you learn why this angle is 105 degrees. So look at it. Positive nucleus, positive nucleus, positive nucleus. So this is the positive side. This is the negative side. So this is like, okay, a polarized atom. So, I don't show you. Sorry. Okay, so here's a model. So again, water, here's water. So we make a model. So we're going to talk about this kind of here and there throughout the semester. A polarized, here's our model. We have a plus, we have a minus, and we somehow assume they're connected. So it acts like a unit. So we call this a dipole. Di means two, right? All right, so okay, plus, minus, somehow we assume they're connected. They're not connected, but it acts as a unit. Okay, so here you go. So you have these dipoles, right? These polarized atoms. They can't, it's an insulator, right? So you can't move from here to here. But what can they do? They can rotate a little bit. So the negative part of the dipole sees this big positive charge. What does it do? Let's say the negative was this. It's going to rotate a little bit. So this is a wild exaggeration, but it's okay. It gets the point across. So they all rotate. So the negative is attracted to the positive. So what happens? So this is kind of, there's going to be like a positive, oops, sorry. So this is going to be like the negative side. This is going to be the positive side. This thing is still neutral, right? But, since this is the negative side, it's going to be attracted. So that's how it works. Okay, so this is what we say. We say large neutral objects are attracted to either a positive charge or a negative charge. And large just means larger than a bunch of molecules. Okay, have you ever seen somebody take a balloon, rub it on their hair so the balloon gets charged, and they stick it on the wall? I mean, the wall is neutral, right? So they have this charged balloon, they stick it on the wall. What does it do? It stays there because of what we just discussed. Okay, so we want to keep talking about our charge model. Charge model. Okay, something else that's very important about charge is it's quantized. What's that mean? It means in the everyday world, if you measure, we always use Q for charge. In the everyday world, if you measure the charge of any normal everyday object, it's always going to be some integer times the charge of an electron. Of course, plus or minus, right? Could be positive, could be negative. So that's what it means to be quantized. I don't want to get over it. Oh, forget it, sorry. Okay, and this is really nothing new. Okay, let's say you go to Foodland and you go up to the clerk and you say, I'd like to buy a half an egg. What's the clerk going to say? You can't do that, right? Because eggs are quantized. They come in units of 1, right? You can only buy n, some integer times 1 egg, right? 1, 2, I don't know, all right? Or how about money? You go to the bank, you ask for a half a penny. Can you get a half a penny? No, because money is quantized. It's in units of pennies, right? Okay, so that's really nothing new. Okay, let's see, forget about the quarks. Okay, now this is, forget it. All right, charge is also conserved. Now, we learned about this in Physics 121. So what does it mean to be conserved? So we talked about energy conservation. So let's say we have some energy and we measure it. Then we do something to the system. Then we measure the energy again. And after, it's the same, right? Or momentum conservation. Momentum before equals momentum after. Well, here what we're saying is that charge is conserved. So let's look at some examples. So here's a neutron, it's neutral. So the charge here is 0. So that means that the charge here better be 0. So this is the neutron decay, right? A neutron decays into an electron, a proton, and something called a neutrino. So 0 charge, okay, here's a negative charge, there's a positive charge, there's no charge. So this charge is 0. So charge is conserved. Okay, how about this? You collide a positron, that's a positively charged electron, with an electron, what's their charge? 0. You get 2 gamma rays, what's their charge? 0. Or here's another thing. So a gamma decays into an E plus E minus. What's the charge? 0. What's the charge? 0. So charge is always conserved. All right. Earlier, we talked about the fact that like charges repel, unlike charges attract. Okay, that's wonderful. But we want to know with what kind of force, right? We want a force law. So that's called Coulombs Law. Because he's the guy who came up with it. Coulombs Law, right? So charges in coulombs, now you know why. So Coulombs Law, okay, Coulombs Law only gives you the magnitude. You have to figure out the direction. So Coulombs Law, the force is a constant K, which we'll get into later. Q1, Q2 divided by the distance squared. So sorry, I forgot to draw it. So here's a Q1, here's a Q2, and here's the distance between them. Right? So it's K, Q1, Q2 over D squared. Where have you seen something like that before? Gravity, right? Remember gravity? So this is an electric force. Gravitational force was G mass 1, mass 2 divided by the distance squared. All right, so K is a constant. So K equals 9 times 10 to the 9th Newton meter squared over Coulomb squared. Now, K also equals 1 over 4 pi epsilon 0. Epsilon 0 is a constant. We'll talk about it later. Why would you want to use this when you can use this? Well, you'll see later on. Later on, it's going to be convenient to use this because we're going to be able to cancel like 4 pi's and 2 pi's and stuff like that. So you really ought to know this. I mean, you're going to use this in your homework, but you ought to know this too because we're going to use it later on. Now, question for you. From your experience using just household objects, how does a gravitational force compare to the electrical force? So, for example, like you've been drying some clothes, and you pull out the clothes, and it sticks to you, right? Now think about it. The entire Earth is pulling down on that article of clothing, but yet that electrical force is strong enough to make it stick to you. So what does that imply? I mean, it implies that the electrical force is way, way, way stronger than the gravitational force. Okay, so let's just do a calculation. Let's look at the hydrogen atom. Where's that stupid? Oh. Now, I said consider household objects, And then I talked about the Earth. So that was kind of a bad example because the Earth is not a household object, right? But that's all right. Okay, so let's look at the hydrogen atom. So hydrogen has a single proton in the middle and an electron going around it, right? So the proton has mass, electron has mass. We can figure out the gravitational force between them. They also have charges. We can figure out the electrical force between them. So I'm just going to show you the answer. Oh yeah, okay, there's Coulombs Law. I already talked about that. Okay, hydrogen. All right, so here's the electrical force law. Here's a gravitational force law that we learned in 121. So you plug in the numbers and look. The electrical force is more than 10 to the 39 times the gravitational force. 10 to the 39! That's a huge number. So, what do you say? When we're doing atomic physics, do we have to worry about gravity? No, because it's tiny. All right, here's a question for you. This is a good review question. Physics 121 all the way. So everybody read it and pause your video and figure it out. Okay, let's do it. So we have two uniformly charged spheres. The charge on sphere 2 is 3 times the charge on sphere 1. What's the correct force diagram? Well, what did we learn in Physics 121? What's Newton's third law? FA on B equals FB on A, right? Equal and opposite. So which one of the force diagrams shows you that? This one, right? Equal and opposite. Don't forget. Equal and opposite. All right. I don't want to do that. Okay, so here's a kind of a typical Coulombs Law problem that you're going to get for this chapter. So the figure shows an arrangement of 6 fixed charge particles. So the A is 2 centimeters, theta is 30 degrees. All 6 particles have the same magnitude, 3 microcoulombs. You know, some are positive, some are negative. What's the net electrostatic force acting on Q1 due to the other charges? So this is just a, 121 force diagram kind of problem, right? So when we did force diagram problems in 121, the first thing we always did was figure out what's the object. So you have to admit, the question says, what's the force acting on Q1? So Q1 is the object. So what we're going to do is we're going to draw Q1, and then we're going to draw the forces acting on Q1. So there's our Q1. All right, now the order doesn't matter. So let's, just for no good reason, let's do or talk about F21. So what's the force that this guy exerts on Q1? Now don't forget Coulombs Law. Okay, so what is a negative going to do with negative? It's going to push it to the right. So this guy's going to be pushed to the right. Now, notice that this is 2A apart, right? And the rest of them are like, a lot of them are just A apart. So the force is going to be to the right, but it's going to be small because the distance is large. So there, all right? So this particle pushes this one to the right with a small magnitude. Okay, let's do F31. Okay, so what's Q3 going to do to that negative charge? Well, unlike charges attract, so force is going to be that way. But look, this is only A, whereas this was 2A. And remember, the law is d squared, right? So this force is going to be 4 times that force. So it's going to be like that. Now, what do we always do with forces that are not along the x or y axis? We resolve them into components. Because remember, how do we always solve these force problems? we always say the sum of the x's equals, whatever, and the sum of the y's equals whatever, right? So we always have to resolve things into x and y. So just get used to it, right? So we're going to resolve it into components. So there's the y piece. This is adjacent, so it's cosine. This is opposite, so it's sine. Okay, let's just keep going. What's this one going to do? What is this going to do? It's going to repel, so down. And it's the same magnitude as this one because it's the same distance. So it's this. All right, we resolve it, bing, bing. What's this one going to do? It's positive, so it's going to attract. And look at it, it's close, so it's going to be strong. So here we go, F61. What's this one going to do? It's going to repel. Well, wait a second. What is this going to do compared to that? They're both going to repel with the same magnitude, right? Opposite direction. So, all right, so here's F41. Okay, so let's do it. So you have to agree, I hope, this cancels that. This cancels that. The angle is 30, sine of 30 is a half. So that plus that is actually going to cancel that. And the net force is, our favorite number, 0. But that's just how you do it. There's nothing new at all. It's just using Coulombs law in your typical forces. Thank you.